Chapter 9, Skeletal System, Articulations, Part 1. So articulations is another word for joints. So basically it is where two or more bones come together. Sometimes it also can include cartilage, or it can include teeth. Teeth are not bones, but primarily it is when two or more bones come together. And the articulations, the various kinds of joints, vary in terms of stability and mobility. So you can have a joint that is extremely mobile, allows for a lot of motions. For instance, the glenohumeral joint, the shoulder joint, allows for a huge range of motions, but it is not the most stable of joints. We've all heard about people dislocating their shoulder. And then at the other extreme, you can have very stable joints, such as the sutures in our skull. It takes a lot to get those to slip out of place. But of course, the sutures in the skull are not at all mobile. They are completely immobile. So again, you can have an extremely mobile joint with lots of motion, or one that's extremely stable, but you can't do both. And there's a range of joints that have different levels of stability versus mobility. Structurally, you can classify joints into three big classifications. First up is fibrous joints. Fibrous joints are joints that are connected by dense, regular connective tissue. Dense, regular connective tissue. These joints are extremely stable, very stable, and allow for little to no movement. So an example of these would be the sutures. The sutures in the skull are fibrous joints that are very stable, very immobile. We also have the syndesmoses. Syndesmoses are stretched out connective tissue connecting bones. So here we have the radius and ulna connected by this sheet of dense regular connective tissue. Allows for a little bit of motion, but not much. And then the gymphoses, this is actually the joints between the skull and the teeth themselves. Next up is cartilaginous joints. Cartilaginous joints, surprise, surprise, are where bones are connected by cartilage. And some cartilaginous joints can allow for some movement, but for the most part, their role is stability. So for instance, the costal cartilage connecting the ribs to the sternum, that is a type of synchondroses. Synchondroses allows for a tiny bit of movement for when we're breathing, but overall pretty stable. Another example is the symphyses, again, thick fibrocartilaginous piece of cartilage connecting the upper and lower vertebra. So intervertebral discs would be an example. The pubic symphysis, another example. Those have a fibrocartilage. And finally is the synovial joints. Synovial joints are the joints that are very mobile. So when you think of a joint, this is usually what you think about because you're thinking about places that allow bones to move. A synovial joint actually has a fluid-filled space that is forming a cavity that separates the articulating bones. The two bones technically are not actually touching. There's this fluid in a synovial cavity separating the bones. This reduces friction at those joints, which is of course good because the less friction, the less wearing and tearing on the joints themselves. And then of course the bones also are connected by ligaments to hold them together more firmly. So here is a generic synovial joint. So in a generic synovial joint, you have the articular cartilage, the hyaline cartilage at the smooth ends of bones where they come together. You have the synovial cavity or joint cavity, that space that is filled with synovial fluid. You also then have the articular capsule, the capsule that is forming the complete joint cavity by connecting and surrounding the space and forming that cavity. And the articular capsule has two layers, a fibrous layer that's more tough, denser regular connective tissue, and a inner layer that is actually epithelial tissue that's going to be producing the synovial fluid. And then, of course, there are always ligaments. So over here is an example of a ligament because you need the stronger connections of the ligaments to hold the bones together for synovial joints. And the synovial fluid is important. It helps to nourish and lubricate the articular cartilage. and it can absorb shocks. So we got some shock absorption from the cartilage itself, from the synovial fluid. We have reduction of friction because of the smooth ends of the bones, the cartilage itself, and again, the synovial fluid. There are additional structures that may or may not be found in a synovial joint. These are optional. You can have additional ligaments connecting the bones. These ligaments can be inside of the synovial joint, inside the joint cavity, or outside of it. You can have tendons involved, tendons that are attaching muscle to bone. You can have bursae. Bursae are fluid-filled sacs filled with synovial fluid. They are positioned in certain areas to limit friction on, say, ligaments or on bones. You can have fat pads, extra fatty material around the joints to provide more cushioning, hold things in place. And of course, you can have fibrocartilage pads. Those pads can be complete circles or they can be half circles. The half circles are known as meniscus. So the menisci in the knee are made of fibrocartilage. In addition, you can have tendon sheaths. Tendon sheaths are similar to bursa. Basically, they're fluid-filled sacs that are stretched out and wrap around tendons. So they're there to protect the tendons from friction, from rubbing against bones. So again, fluid-filled sacs that completely go around the tendons. All right, synovial joints get broken down to a number of classifications, and this depends on the shapes of the articulating surfaces and by the amount of movement allowed. So two categories coming together in classifying synovial joints. So first up is the pivot joint. The pivot joint is uniaxial, so it only allows for a limited single kind of motion, and this is going to be a rotational motion. And then you have a rounded surface that fits into a ring. So here in the atlantoaxial joint, we have the dens that is being fitting into a ring made up of the atlas and ligament. And this allows for lateral rotation of the head. So we can turn our head to say no. Hinge joint. Hinge joint, also uniaxial, only allows one kind of motion, flexion, extension. Here we have a convex bone, a rounded bone fitting into a concave surface, a depression-like surface. So here's, of course, the humerus fitting into the trochlear notch of the ulna, the head of the radius. So the elbow is an example of a hinge joint. We have planar joints. Plane joints, also uniaxial. They only allow for one kind of motion, a side-to-side movement, sometimes referred to as gliding. And uniaxial, also, they are composed of flat surfaces. So two bones coming together, and overall the surfaces meeting together are flat. So an example is the intercarpal joints, the different joints between the carpals themselves. Those are plane joints, not very mobile, but do move a little bit in a side-to-side manner. Again, flat surfaces. Then we have the saddle joint. Saddle joint is biaxial. Biaxial, two kinds of movement, basically. So the main movements in a saddle joint is flexion, extension, and abduction, adduction. We'll go into those movements a little more in the second video. And also circumduction, which is kind of a combination of these four. So again, we have a convex bone, a rounded sort of bone fitting into a concave bone. Here, though, it looks a little bit like they are interlocking. Looks a little bit like you got a saddle with some person's legs coming down on either side, vaguely. Back when everyone had horses, saddles was a great thing to compare things to. So an example of this is the Carpo metacarpal joints. So where the metacarpals make contact with the carpals, and the best example is where the first metacarpal makes contact with the trapezium. That's the joint for the thumb that would allows the full range of motion of the thumb. Condylar joints. Condylar joints are also biaxial. Here you got more oval convex surface fitting into a concave surface. So again, a nice rounded knob fitting into a bowl-like depression. Here, again, two main kinds of motions. We have flexion, extension, and abduction and adduction. Again, circumduction is kind of a combination of those four movements. An example here is the metacarpal phalangeal joints, so the joints between the proximal phalange and the metacarpal. Then we have the ball and socket joint. Ball and socket joint is the multi-axial joint. Multi-axial, many kinds of motions allowed. Here we have a sphere-like head, very super rounded head, fitting into a cup-like surface. So the head of the femur fitting into the acetabulum of the os coxae is a great example. Also, the glenohumeral joint or shoulder joint is another great example. So motions include flexion, extension, and hyperextension, abduction, adduction, circumduction, lateral rotation, and medial rotation. So we get the rotations as well as flexion, extension, hyperextension, abduction, adduction. Large range of motions. Levers. So lever systems is basically what our joints are creating in the biological environment. However, levers are a bit more well understood in physics. So we're going to talk a little bit about levers in general. So you have to have the lever itself, which is a rigid rod of some kind. So our body, that's the bones. You have to have a place where the movement is occurring, where the lever's rotating around. And for our body, that is the joints. For a lever system, that's referred to as a fulcrum. So the fulcrum is where the joint is. And then the fulcrum is great because it allows the ability to affect the speed and distance of movement produced by any force, as well as the direction of the applied force. So by pushing on the lever system, you can cause movement at the fulcrum that then moves the other end of the lever. So effort. Effort is the force being applied, the muscles contracting or producing the effort. The resistance is what we're moving. The resistance can be a thing physically external to us. It can just be part of our body. It is whatever it is we're trying to move. And we get movement if the effort exceeds the resistance. Now, you can have mechanical advantage or mechanical disadvantage. Mechanical advantage means the fulcrum is closer to the resistance, and that means it's easier to cause movement. Mechanical disadvantage, the fulcrum is closer to the effort, and that actually means it's going to be more difficult to move. So you would automatically think that you're going to want a mechanical advantage, but our bodies are weird. So this example here with the seesaw, 3 meters, the fulcrum is 3 meters from the effort, 1 meter from the resistance. So pretty clearly this is a mechanical advantage. So the 3 main classes of levers. You have the first class lever. First class lever has the fulcrum in the center. So basically like our seesaw example. And the fulcrum is in between the resistance and the effort. It's relatively uncommon in our body. We have an example of it at the atlanto-occipital joint in the neck, where the occipital bone makes contact with the atlas, and that's the joint that lets us move our head to nod yes. So that would be first class lever. And another example in the real world would be a pair of scissors, would be another example. Now, is this a mechanical advantage or a disadvantage? Well, it turns out it depends. It depends on the placement of the fulcrum relative to the resistance and the effort. So it could be an advantage if it's closer to the resistance, or it could be a disadvantage if it's closer to the effort. Second class levers, you have the resistance is now between the fulcrum and the effort. So an example of this would be, say, a wheelbarrow where the wheel is the fulcrum, resistance is what you're carrying, effort's pulling on those bars. It is pretty rare in the human body. One example is when we stand on tiptoe, that would be a second class lever. And the fulcrum is automatically closer to the resistance, so this is always a mechanical advantage. Class 2 levers are always a mechanical advantage, and yet it's rare in our body. Then we have third class levers. Third class levers have the effort between the resistance and the fulcrum. The effort between the resistance and the fulcrum, which means that the fulcrum is always closer to the effort, which means it is always a mechanical disadvantage. Always have to put more effort in, more energy in than you would otherwise to move the resistance. Most common in our body, example is the elbow joint, and it turns out that the reason why this is the most common one is because it allows for a faster response and a larger range of motions. So we do it because it has other advantages. And that's it for this part of the lecture.